The era of 1-bit LLMs. All large language models are in 1.58 bits. Abstract. Recent research, such as BinNet 2023, is paving the way for a new era of 1-bit large language models. In this work, we introduce a 1-bit LLM variant, namely BinNet 1.58, in which every single parameter or weight of the LLM is ternary, -1, 0, 1. It matches the full precision that is FP16 or BF16, transformer LLM with the same model size and training tokens in terms of both perplexity and end-task performance, while being significantly more cost-effective in terms of latency, memory, throughput, and energy consumption. More profoundly, the 1.58-bit LLM defines a new scaling law and recipe for training new generations of LLMs that are both high-performance and cost-effective. Furthermore, it enables a new computation paradigm and opens the door for designing specific hardware optimized for 1-bit LLMs. Figure 1. 1-bit LLMs, for example, BinNet 1.58, provide a Pareto solution to reduce inference cost, latency, throughput, and energy of LLMs while maintaining model performance. The new computation paradigm of BinNet 1.58 calls for actions to design new hardware optimized for 1-bit LLMs. 1. The era of 1-bit LLMs. In recent years, the field of AI has seen a rapid growth in the size and capabilities of large language models, LLMs. These models have demonstrated remarkable performance in a wide range of natural language processing tasks, but their increasing size has posed challenges for deployment and raised concerns about their environmental and economic impact due to high energy consumption. One approach to address these challenges is to use post-training quantization to create low-bit models for inference. This technique reduces the precision of weights and activations, significantly reducing the memory and computational requirements of LLMs. The trend has been to move from 16 bits to lower bits, such as 4-bit variants. However, post-training quantization is suboptimal, even though it is widely used in industry LLMs. Recent work on 1-bit model architectures, such as BitNet, presents a promising direction for reducing the cost of LLMs while maintaining their performance. Vanilla LLMs are in 16-bit floating values, i.e., FP16 or BF16, and the bulk of any LLMs is matrix multiplication. Therefore, the major computation cost comes from the floating point addition and multiplication operations. In contrast, the matrix multiplication of BitNet only involves integer addition, which saves orders of energy cost for LLMs. As the fundamental limit to compute performance in many chips is power, the energy savings can also be translated into faster computation. In addition to computation, the process of transferring model parameters from DRAM to the memory of an on-chip accelerator, e.g. SRAM, can be expensive during inference. There have been attempts to enlarge SRAM to improve throughput, but this introduces significantly higher costs than DRAM. Compared to full-precision models, 1-bit LLMs have a much lower memory footprint from both a capacity and bandwidth standpoint. This can significantly reduce the wait time of loading weights from DRAM, leading to faster and more efficient inference. In this work, we introduce a significant 1-bit LLM variant called BitNet B1.58, where every parameter is ternary, taking on values of -1, 0, 1. We have added an additional value of 0 to the original 1-bit BitNet. Results have shown that the modified 1-bit BitNet B1.58 retains all features from the original 1-bit BitNet, including its new computation paradigm, which requires almost no multiplication operations for matrix multiplication and can be highly optimized. Additionally, it has the same energy consumption as the original 1-bit BitNet and is much more efficient in terms of memory consumption, throughput, and latency compared to FP16 LLM baselines. Furthermore, BitNet B158 offers two additional advantages. Firstly, its modeling capability is stronger due to its explicit support for feature filtering, made possible by the inclusion of 0 in the model weights, which can significantly improve the performance of 1-bit LLMs. Secondly, our experiments show that BitNet B158 can match full precision, i.e., FP16 baselines in terms of both perplexity and end-task performance, starting from a 3B size when using the same configuration, e.g., model size, training tokens, etc. 2. BitNet B158. BitNet B158 is based on the BitNet architecture, which is a transformer that replaces NN.linear with BitLinear. It is trained from scratch with 1.58-bit weights and 8-bit activations. Compared to the original BitNet, it introduces some modifications that we summarize below. Quantization function. To constrain the weights to -1, 0, or +1, we adopt an absmean quantization function. It first scales the weight matrix by its average absolute value and then round each value to the nearest integer among -1, 0, +1. The quantization function for activations follows the same implementation in BitNet, except that we do not scale the activations before the nonlinear functions to the range 0 to QB. Instead, them activations are all scaled to QP per token, to get rid of the 0-point quantization. Table 1. Perplexity as well as the cost of BitNet B158 and Llama LLM. Table 2. Zero-shot accuracy of BitNet B1.58 and Llama LLM on the end tasks. This is more convenient and simple for both implementation and system-level optimization, while introduces negligible effects to the performance in our experiments. LLama-alike components. The architecture of LLama has been the de facto backbone for open-source LLMs. To embrace the open-source community, our design of BitNet B158 adopts the Llama-alike components. Specifically, it uses normformer, SWI-glue, rotary embedding, and removes all biases. In this way, BitNet B158 can be integrated into the popular open-source software with minimal efforts. 3. Results. We compared BitNet B158 to our reproduced FP16 Llama LLM in various sizes. To ensure a fair comparison, we pre-trained the models on the Red Pajama dataset for 100 billion tokens. We evaluated the zero-shot performance on a range of language tasks, including ArcEasy, ArcChallenge, HelloSwag, Winagrand, Pika, BookQA, and BoolQ. We also reported the validation perplexity on the Wikitext2 and C4 datasets. We compared the runtime GPU memory and latency of both Llama LLM and BitNet B158. The results were measured using the Faster Transformer codebase, which is well optimized for LLM inference latency on GPU devices. The 2-bit kernel from Ladder is also integrated for BitNet B158. We reported the time per output token, as it is the major cost for inference. Table 1 summarizes the perplexity and the cost for BitNet B158 and LLM. It shows that BitNet B1.58 starts to match full precision LLM at 3B model size in terms of perplexity, while being 2.71 times faster and using 3.55 times less GPU memory. In particular, BitNet B1.58 with a 3.9B model size is 2.4 times faster, consumes 3.32 times less memory, but performs significantly better than Llama LLM3B. Figure 2. Decoding latency, left, and memory consumption, right, of BitNet B1.58 varying the model size. Table 3. Comparison of the throughput between BitNet B1.5870B and Llama LLM70B. Table 2 reports the detailed results of the zero-shot accuracy on the end tasks. We followed the pipeline from LM evaluation harness to perform the evaluation. The results show that the performance gap between BitNet B1.58 and Llama LLM narrows as the model size increases. More importantly, BitNet B1.58 can match the performance of the full precision baseline starting from a 3B size. Similar to the observation of the perplexity, the end task results reveal that BitNet B1.58 3.9B outperforms Llama LLM 3B with lower memory and latency cost. This demonstrates that BitNet B1.58 is a Pareto improvement over the state-of-the-art LLM models. Memory and latency. We further scaled up the model size to 7B, 13B, and 70B and evaluated the cost. Figure 2 illustrates the trends of latency and memory, showing that the speedup increases as the model size scales. In particular, BitNet B1.58 70B is 4.1 times faster than the Llama LLM baseline. This is because the time cost for NN linear grows with the model size. The memory consumption follows a similar trend, as the embedding remains full precision and its memory proportion is smaller for larger models. Both latency and memory were measured with a 2-bit kernel, so there is still room for optimization to further reduce the cost. Energy. We also estimate the arithmetic operations energy consumption of both BitNet B1.58 and Llama LLM. We focus mainly on the calculation for matrix multiplication, since it contributes the most to the cost of LLMs. Figure 3 illustrates the composition of the energy cost. The majority of BitNet B1.58 is an 8 addition calculation, while LMA LLM consists of both FP16 addition and FP16 multiplication. According to the energy model in HOR 14, ZZ22, BitNet B1.58 saves 71.4 times arithmetic operations energy consumption for matrix multiplication on 7nm chips. We further reported the end-to-end energy cost for models with 512 tokens. Our results show that as the model size scales, BitNet B1.58 becomes increasingly more efficient in terms of energy consumption compared to the FP16 LLM baseline. This is due to the fact that the percentage of NN.linear grows with the model size, while the cost from other components is smaller for larger models. Throughput. We compare the throughput of BitNet B1.58 and LLM with 70B parameters on two 80GB A1000 cards, using pipeline parallelism HCB plus 19 so that LLM 70B could be run on the devices. We increased the batch size until the GPU memory limit was reached, with a sequence length of 512. Table 3 shows that BitNet B1.5870B can support up to 11 times the batch size of LLM, resulting in 8.9 times higher throughput. Figure 3. Energy consumption of BitNet B1.58 compared to LLM at 7 nanometer process nodes. On the left is the components of arithmetic operations energy. On the right is the end-to-end energy cost across different model sizes. Table 4. Comparison of BitNet B1.58 with stable LM3B with 2T tokens. BitNet B1.58 is enabling a new scaling law with respect to model performance and inference cost. As a reference, we can have the following equivalence between different model sizes in 1.58-bit and 16-bit based on the results in Figure 2 and 3. 13B BitNet B1.58 is more efficient in terms of latency, memory usage, and energy consumption than 3B FP16 LLM. 30B BitNet B1.58 is more efficient in terms of latency, memory usage, and energy consumption than 7B FP16 LLM. 70B BitNet B1.58 is more efficient in terms of latency, memory usage, and energy consumption than 13B FP16 LLM. Training with 2T tokens. The number of training tokens is a crucial factor for LLMs. To test the scalability of BitNet B1.58 in terms of tokens, we trained a BitNet B158 model with 2T tokens following the data recipe of stable LM3B TBMR, which is the state-of-the-art open-source 3B model. Both models were evaluated on a benchmark that consists of Winogrand, Pika, SciQ, Lambda, and ArcEasy. We reported the zero-shot accuracy in Table 4. For tasks measured with accuracy and normalized accuracy, we take the average of the two. The results of stable LM3B at 2T tokens are taken directly from its technical report. Our findings shows that BitNet B1.58 achieves a superior performance on all N tasks, indicating that 1.58-bit LLMs also have strong generalization capabilities. 4. Discussion and future work. One-bit mixture of experts LLMs, mixture of experts MOE, have proven to be a cost-effective approach for LLMs. While it significantly reduces the computation flops, the high memory consumption and inter-chip communication overhead limits its deployment and application. These challenges can be addressed by 1.58-bit LLMs. Firstly, the reduced memory footprint reduces the number of devices required to deploy MOE models. Moreover, it significantly reduces the overhead of transferring activations across networks. Ultimately, there would be no overhead if the entire models could be placed on a single chip. Native support of long sequence in LLMs. In the era of LLMs, the ability to handle long sequence has become a critical demand. One major challenge for long sequence inference is the memory consumption introduced by the KV caches. BitNet 1.58 represents a significant step towards native support for long sequences, as it reduces the activations from 16 bits to 8 bits, allowing the context length to be doubled given the same resources. This can be further losslessly compressed to 4 bits or even lower for 1.58-bit LLMs, which we leave as future work. LLMs on edge and mobile. The use of 1.58-bit LLMs has the potential to greatly improve the performance of language models on edge and mobile devices. These devices are often limited by their memory and computational power, which can restrict the performance and the scale of LLMs. However, The reduced memory and energy consumption of 1.58-bit LLMs allows them to be deployed on these devices, enabling a wide range of applications that were previously not possible. This can greatly enhance the capabilities of edge and mobile devices and enable new and exciting applications of LLMs. Moreover, 1.58-bit LLMs are more friendly to CPU devices, which are the main processors used in edge and mobile devices. This means that BitNet 1.58 can be efficiently executed on these devices, further improving their performance and capabilities. New hardware for 1-bit LLMs. Recent work like Grok 3 has demonstrated promising results and great potential for building specific hardware, for example, LPUs for LLMs. Going one step further, we envision and call for actions to design new hardware and systems specifically optimized for 1-bit LLMs, given the new computation paradigm enabled in BitNet. This concludes the reading of the era of 1-bit LLMs. All large language models are in 1.58 bits, on research to you. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.